Hello, Mr. Ryan. How are you today?
Good.
So, can you remind me what's a binary tree?
A binary. With numbers.
Numbers. Can you draw a binary tree, please?
I will draw.
It's not numbers. It's a tree, you know, but with the numbers. Yes.
Upside down tree.
Yeah. And where is the root?
At the very top.
Okay. Can you also maybe you can make a binary search tree? Do you remember?
Oh yeah.
Oh, can you make a binary search tree?
Oh, that'll be.
Obviously, binary search tree is one kind of binary tree. Okay. Yeah. And that's we're done.
I'll put.
Okay.
I'll put 2.
Okay, so can you explain to me what is this binary search tree?
So the left one is smaller than
the root and the right one is bigger. Yes,
yeah.
Strictly bigger. So look, all the nodes in the left tree are strictly smaller than 4, right?
Yeah.
So even this, if you can put an A here because A is bigger than the 4, right?
Yeah.
Even is satisfied, A is bigger than 2. So all the left trees must be smaller than the parents. All the right tree must be bigger than the right.
Only one node.
Yeah, that's very good. Okay, so.
Oh, like no one.
No, that's it. So how about look if let's say Eric is 7 and Ryan.
8.
Okay, 8. 8. Okay, 8 and Ryan is what?
I'm 7.
Then I can't put a. Let's pretend you are 2. Okay. Can I? Because it doesn't satisfy the binary search tree. Is that okay?
I can make one.
Okay.
I can make one.
Let me do it. Let me do it. Let me do. Okay, let me put it 7. Okay. 7. Okay. But this does not satisfy. Though. Let's change this to 7.5. Right? And then this needs to be bigger. Let's put it at 7.2. Okay. And then that will be 1. Okay. That's a binary search tree. And then 7 is Ryan. Eric's is 8. Is that okay? Yeah.
My parent is 7.5.
Okay, that's fine. Okay, so now the target is that if I give you, if I want to find the sibling, you know the sibling? Brothers, yeah, brothers, sisters, sibling. Okay, so suppose I want to find the brothers of Eric. I need to tell me this, right? And I want to find the brother of Ryan is Eric, right?
I'm the oldest.
Sibling. Okay, so. How do you search this? How do you do this? What's the idea? How are we dealing with this problem? So basically, it's finding the sibling in a binary search tree. Okay, remember it's binary search tree. How are we using this binary search tree? But first of all, how are we finding a node in a binary search tree?
We start from the root.
Yeah.
If it's smaller, you go to the right.
Which one is smaller? Go to the right.
Oh yeah. If the one you're looking for is
smaller,
you go to
Don't need to project a long time.
No, go to the right. Go to the left. Because you are look. For example, you are not. You want to find Eric, which is bigger. Go to the right. You want to find Ryan, which is smaller. You go to the left. Right?
Oh yeah.
Yeah. Okay. So this. What's the time complexity of this one? If there are n trees in the binary.
N nodes.
Sorry, n nodes in the binary search tree. Or. Are you sure? We are using the binary search tree.
Where?
If the tree is highly balanced, highly balanced, right? So in the worst case, if it's not highly balanced, it's O(n). But in the optimum case, no. In the optimum, I mean the tree is highly balanced. Every time I cut into the search space by 2, so what's that?
N divided by 2.
No, we're not talking about a constant here. So every time I cut, look, if there are 8 nodes, every time I search it, I cut into 2, then I search 4 nodes. And I make one check and I search to 2. So what's this kind of thing? Every time I cut into the half. Remember? Remember the binary search? Remember? Every time?
Log(n).
Yeah, we're done log(n).
Yeah! My favorite one.
Yeah, log(n). Yeah. If the tree is highly balanced.
If
not highly balanced, what's the term complexity?
O(n).
Why is that? Can you give me an example? In what cases it's not?
One's like this.
Yeah, well done. It's like a linked list because the binary search, it can be still a binary search tree, and it will be like 1, 2, 3, 4. But in order to search 4, you need to find 4 times. Yeah, yeah. Does it make sense?
Yeah.
So this is not making use of the binary search tree, the characteristics of that. Okay, so now. So we know how to search the node in the binary search tree.
Yeah.
How about we search the sibling? So when we go to the brother. So look, we know we look for Eric, right?
Yeah.
So we know it's on the left side, right? But before we go to the left side, we know the brother of Eric. Of the next node is right? Do you get it?
Yeah.
So we just need to add one more step, is that before we go to the left or go to the right, we remember the brother node of the node you want to visit next, right? And suppose, okay, here, I found a Ryan here, right? But before I come here, I know this node's brother is Eric, so I can find it, right? Because in binary trees, you only have 2 kids, am I right?
Yeah.
Does it make sense?
Yeah.
Okay, so
You're supposed to be this one.
yeah. Okay, so this has an assumption that the brother node always exists. Okay, so what does it mean? It means that the binary tree will have each node will have 0 or 2 children. Okay, does it make sense?
Yeah.
Okay, so we can do it. Look, let's do this. Okay, you tell me what to do. Okay, define. Let's do find brother. Okay, find brother.
Find brother.
Okay, find.
That has to be brother.
Okay, I see it anyway. Root, and let's find this what? Maybe let's name it Eric. Okay.
Me.
Okay.
Callum.
Okay. Or Ryan. Okay. It doesn't matter. Okay? So given Eric, we want to find Ryan. Yeah. Okay. Is that okay? Yeah. Okay. So now look. If
Where?
no, we're not going to, because we know Ryan is there. So and the root is not empty. So let's skip for now. So let's say while root. You know while root. Then let's say wait. Sibling. Let's do the answer. Okay. Maybe let's do the Ryan. Ryan equals none. Beginning we haven't found it. Yeah. Ryan equals none. Now while root. If root dot value is Eric. Eric, look.
It's Eric.
And then what should we do? If you found the root, if common root is Eric, then we return Ryan, right? Because Ryan is here, right? Ryan is there, yeah? Yeah? Does it make sense?
Yeah.
Okay, now look. If root dot value is smaller than Eric. So what does it mean? So the Eric is bigger than the current root. So look, Eric, this is 7.5, right?
Eric.
You are looking for Eric, 8, yeah? So 8 is bigger than 3.5. So what do we do?
That's 7.5. We go to the
Right.
Yeah.
So then how do we go to the right? Root equals root of what?
Root of value, I think.
Root of right. Yeah?
Root of right.
And then because we go to the right, so we know we need to update the Ryan to the left, right? Am I right?
Yeah.
Does it make sense? So here will be Ryan equals what? Can you tell me? And else, what should we do?
Ryan.
Return what? Can you feel this? Does that make sense? Look.
Answer here.
No, there's no answer. Come on. Look.
Ryan.
Yeah, Ryan. Okay, here. But here, root equal. Look, we are here, root now, and we're going to the right. Now, look, we're going to the right. This is possibly could be Eric here, right? And where's the Ryan? Where's the Ryan?
On the left.
So before this.
Possibly.
So look here, Ryan equals what?
Ryan equals
root of what?
left.
Okay, root of that. There's a problem here. Because it always changes root, so this has to be here, right? So Ryan equals root of left, and then I go to the here, right? Am I right? Does it make sense? Does it make sense?
Yeah.
Okay, so here about this one.
Return me.
So look, this one. Root of value, if it's bigger than Eric, what should we do? Eric?
What?
Then here. So if it's on the left hand side, so what should we do?
No.
What?
Ryan?
Equals what?
Root of 5.
Well done, and then? And then what? And then Ryan is here, but we need to go to the left hand side, so what?
Root equals root of right. No, root of
The what?
left.
Left. Yeah, always go to the opposite, okay?
Yeah.
Okay, what's the time complexity? What's the time complexity?
N.
Come on, it's the same as the previous.
Nothing.
Okay, log in, come on. We are adding just extra bit. Ryan here.
Extra bit.
Ryan here.
Lion.
Look, if we are not, look, it's almost the same as searching a node in the binary tree, except that we are returning Ryan, not returning Eric here, right? Right? We are returning Ryan. Look, if you get rid of these, then it's the same. It's basically the same as searching a node in the binary search tree, but we are returning the parent and the Ryan's node. Okay. So how do we update the Ryan's node? Every time we go to the left, we update the Ryan's node on the right. Every time we go to the right, we update the Ryan's on the left. Yeah.
Yeah.
Okay. Can we do this using the recursion?
Cash.
No. No. We don't need recursion. Let's do it. Let's do this. Okay, I show you. Look, it will be similar. Okay. Define. Let's do this time. Find Ryan. Okay. How about that? Yeah.
Find Ryan.
Find Ryan. Find
Ryan.
brothers. Okay. Find brother, and then that will be root.
You should
Ryan.
do find Sibling.
What's missing?
Column.
Okay. And then let's do a search function here. Define. Look, Eric. Find. And then let's add one more parameter here, right? Because we need to know past the sibling, okay? So let's say root. We are finding the Ryan and we are passing the sibling, which is
Ow.
okay? Yeah, got it? What's missing?
Column.
Yeah. Okay.
Most times.
Okay, now at the beginning,
Not every time.
every
Like
beginning,
the
look,
most.
return. Eric,
No.
return. Find. We want to find the root with the Ryan and Eric, okay? Eric is the sibling, okay? Just to make it.
Sibling.
This is the current sibling. We are returning
Eric
the.
loves R.
Okay.
E.
Look. If current root is
I'm here.
if current root is Ryan, what should we do? If current root is
Eric.
well done. Wow, that's great.
Yeah.
Yeah. Return Eric. Yeah.
I'm
Okay.
gonna shift.
That's good. Eric. Now look, if root, okay, let's say if root equals, let's Eric, if root value is smaller than Ryan,
Return Ryan.
no,
Eric.
no. If it's smaller than Ryan, look, if Ryan is bigger than the root, so
Return me.
where is the Ryan? Ryan is in the right tree or left tree. Remember?
Left.
Look, this is
Right.
the root.
Right.
And then
Right.
Ryan is bigger than root, so it's in the what? Right, yeah?
Yeah.
And then return. Look, return find. Eric. And then we do this root or what? Dot right. And we still passing the Ryan. And then what should we passing here? Ryan will be root the left, right? Eric,
What?
you're not paying attention
I
again.
am.
Okay, so look. Return find, root the right.
Ow.
What should I put here? Come on.
Column.
No.
You
What?
have a closed bracket.
Look, we are going to the right.
Return.
We are going to the right with the find
Eric.
function. No. Can I ask you to be a good boy?
I am.
Return find root dot right. We're going to the right. We want to find the right. And we want to find what's Eric value now?
Me.
No. What's Eric? It's root dot what?
Right.
Root dot right. We are going to the root of left. Come on. Root of left. Alright. And then return here will be the other direction. Find the root of what?
Find the root dot.
It's on the left side. Left. And then Ryan. And then what's the sibling of this passing?
Eric.
What's Eric? Come on, I need to update Eric.
Root dot. Eric. Left.
We are going to left, right, come on. Does it make sense? Does it make sense?
Yeah.
Okay, I'm going to erase some of you, okay? Can you please? Please, not here, maybe I write it again and then you tell me, okay?
What?
Define, find, okay? Find brother.
Brother, read.
Luke.
Ryan.
Okay, you want to find the Ryan, okay?
Colin.
Wire something, okay?
Right.
Okay, that's good. If Luke
Okay, that's good.
equals, okay, let's have Eric here. Eric is none. Okay. If
I'm
Luke
none.
equals Ryan, if Luke equals Ryan, return.
Me.
Return what?
Eric.
Eric. Okay. If Luke dot no value, okay, equals big. If Luke is smaller than Ryan, do this. Else, do this. Okay, there are two here, two things here. Can you write it?
Something with D, something with D return.
Yeah, I can write one for you. If Luke and smaller than Ryan, then Eric would be equals what?
I think the line is more longer than that.
Yeah, I know. Luke dot what? And then left or right. Ryan is bigger than the Luke, so Ryan is on the right hand side, so Eric is left hand side. And then what should we do here? Luke, we are going Luke dot left or right?
White.
Yeah, okay. And then can you write this? Here.
Eric
Yeah, Eric equals.
equal root dot white.
Okay, and then what's next?
Root equals root dot white.
Huh?
Left.
Left, come on! And then we can return Eric here. If Eric is not found, if Ryan is not found in the tree, what should we do?
Return it.
Return Eric here because it's none, right? If Ryan is not found, and then this loop will be ended, and then we'll return Eric, right? Does it make sense? Or return none. I think it will be return none, which is better. Return none. Because if Ryan is not found, we return none. It means that the brother of Ryan is not there, right?
Yeah.
Okay, what's the time complexity?
Or log n.
What's the space complexity?
Oh, log n.
No. Do we use the extra space here?
1.
Oh, 1. Yeah, we're done. Okay, so can we say bye-bye to people?
Bye-bye.
Have a good weekend.